Now let's take a look at example 4.5. This example is similar or almost identical to example 4.2, where we explored the linear kinematics of a train moving between two stations. Now, this example says that starting from rest, a wheel accelerates uniformly to 300 revolutions per minute, or RPM in short, in 5 seconds. So the train accelerates uniformly to 300 RPM in 5 seconds. After rotating at 300 RPM for some time, it retards uniformly to rest in 20 seconds. So the total number of revolutions, that means the angular displacement made by the wheel, is 500 revolutions. So first and foremost, we notice that there are two non-SI units, RPM as well as revolutions. So we need to convert them to SI units. One revolution is 2 pi radian. 500 revolutions will be equal to 500 times 2 pi, which is 1000 pi radians. Next, we have to convert the 330 RPM. Now, we have to convert revolution per minute to radians per second. As what I've shared during the lecture, all you need to do is to pen down the units that you want to convert, and looking at the larger quantity, you just put 1 over there. In this example, 1 revolution. 1 revolution is equal to how many radians? 2 pi. 1 minute, 60 seconds. With this relationship established, just substitute the non-SI unit of interest that you want to convert into the original form. And there you have it. 30 revolution per minute is actually equals to 30 times 2 pi over 60 radians per second. And the equivalent will be 10 pi radians per second. So with the units converted, we can move on to solve the problem. Again, example 4.5 is similar to example 4.2, just that the 4.2 example, we were the train. We imagine we were the train traveling between two stations. But in this example, now from the train, we becomes the wheel. So now we are the wheel rotating along a displacement. Now, first part, they ask us to sketch the angular velocity time graph. So again, example 4.2, we are plotting the VT graph, the linear velocity. Now it becomes the angular velocity because now our motion is angular. So the y-axis will be omega radian per second. Now, what are the information given in the problem? It says that the total number of revolutions made by the wheel is 500 revolutions. So we have converted that to 1000 pi radians. So the angular displacement theta is equals to 1000 pi radians. Next, the problem says that the wheel starts from rest and accelerates uniformly in 5 seconds to an angular velocity of 10 pi radians. Thereafter, it maintains at this particular angular velocity for a certain time t, which we assume as t along the time axis. Thereafter, in 20 seconds time, it decelerates to a complete stop. And this is the angular velocity time graph for the wheel. Part B, we are asked to determine the time taken when the wheel is rotating uniformly at 300 revolutions per minute. So we are referring to this time frame. Yeah. So how do we solve this? Well, for a start, we know that the total angular displacement theta is 1000 pi. What does that imply? It implies that the area under the omega t graph is equal to 1000 pi radians. So putting that down, total displacement of the wheel is equals to 1000 pi, which is equal to the area under the graph, which is the area of a trapezium. And just plugging in the values, A is equals to t minus 5, B is t plus 20, as shown in the time axis, times the height, which is 10 pi. And solve this equation, we will get or determine t is equals to 92.5 seconds. But the question is asking us the time taken when the wheel is rotating uniformly at 10 pi radians per second. That's why we have to use t minus 5 equals to 87.5 seconds. And part B, part 2, we are asked to find the angular retardation. Now, again, retardation is the same as deceleration. We'll solve it using the angular acceleration formula, which is alpha equals to final angular velocity minus initial over time taken. So for the final velocity, angular velocity, it is 0. Initial is 10 pi radians per second over the time taken, which is 20. And there you have it, the retardation. The angular retardation is equals to 1.57 radians per second square.